All right, this week we're going to look at concentration and a few other things. There are 5 ways we calculate concentration, and you are responsible for all 5 of these. The first 3 are fairly straightforward. The 4th one is tough only because it's kind of the big number, little number idea again. And then lastly, molar concentration, which we're going to use primarily for the rest of the unit. All right, so let's go through these. First one is mass by volume percentage. All right. So now we're going to take the mass of the solute divided by the volume of the solution, which is mass, or the solute, volume of the solute and the solution together, and multiply that by 100%. Okay. This one's kind of a wonky one because the units are different. And because the units are different, it's very easy to have misleading information given with this one. You have to know something about what you're dealing with or in order for the percentage value to actually make some sense. This one is quite often used by, for example, shampoo companies. They say there's such and such a percentage of this particular ingredient in a mass by volume percentage, and it turns out that the percentage is really quite high because of this difference in units. Not that it actually means much, but it can be misleading. The other problem with it too is you can easily have values greater than 100%, which also again is sometimes quite misleading. An example of this would be if a pharmacist adds 2 milliliters of distilled water to 4 grams of a powdered drug, making the final volume 3 milliliters. What's the percent mass by volume in the solution? All right, so for this kind of question, normally I would do this on the board, and we would work it out. So 2 divided by 4. 4 grams divided by 3 milliliter volume times 100%. It gives you 133.33%. And so you can see here, this is an example where quite easily it's more than 100%. All right, second way is very similar to the first, except now we're dealing with similar mass units. So it's the mass percent. So the mass of the solute by the mass of the solution times 100%. Same idea. Calculation is done exactly the same way. Here's an example. Sodium fluoride, you have that in toothpaste. If you have a 50 gram sample of the toothpaste, so that's going to be our solution. What mass is in there? That'll give you a 0.76% concentration, mass by mass. Okay, so again, set up the equation, plug in what you know, rearrange the equation to solve for the mass of the mass of the sodium fluoride, and so then we end up with 0.38 grams. All right, the third method is the volume by volume percent. So again, same idea, similar units. This time it's milliliters and milliliters. We could change this to liters and liters, but as long as the units are the same, you're good. Again, it's the volume of the solute, the volume of the solution. All right, so rubbing alcohol is sold as 70% volume of alcohol in water. What volume of alcohol is used to make 50 milliliters of the rubbing alcohol? Set up our equation. Again, we're solving for the volume of the alcohol this time. And we get 350 milliliters. Okay. Now another part of this question would be then, so how much water do I have to add to the solution? So that would be just the difference between these two. So we would have 150 milliliters of water. Okay. Question 4 is very similar, or sorry, the fourth one is very similar to the second one. It's a mass by mass, but rather than using percent, where we multiply by 100, we're now going to use parts per million, parts per billion. So we're going to multiply by 1,000,000 and multiply by 1 billion instead. That's the only difference. And if you can wrap your brain around that, it makes this a whole lot easier. Okay, so it's a mass of solute, again in grams, mass of solution, again in grams. But the difference now is we're multiplying by 1,000,000 times 10 to the 6. Or in the case of parts per billion, times 10 to the 9. Okay. That's the only difference, right? The percent mass by mass is times 100. So this is the only part that's a little bit different in the way we use these calculations. But for some reason, students find parts per million, parts per billion really confusing. Don't know why. All right, use this stuff for really, really small concentrations. Okay, so if you had like 0.00027 percent, why use such a small number? Why not go to parts per million or parts per billion, right? Excuse me. All right, so let's use this as an example. So mercury levels above half of parts per million are kind of lethal. So if we have a fish that's 2 kilograms, what is the mass of mercury that's considered to be dangerous? So again, set up our equation, plug in what we know, the 0.5 parts per million, mass of the mercury times 10 to the 6 divided by 2,000 grams. All right. Then the mass of the mercury, rearranging all of this, we get the 0.5 parts per million times the 2,000 grams divided by the 10 to the 6, and we get 0.001 grams. Okay, now it's important that you know what your units are here. Okay, and then quite often when you end up with a really, really, really small mass, you convert it to something that's easier to deal with, like milligrams, right? So multiply it by 1,000 or 1,000,000 or something like that. 1,000,000 would be micrograms, right? Okay, and the last one we're doing is molar concentration, and this is the one we use most often in class. This is where we look at the number of moles of the solute divided by the volume of the solution, and the volume is always in liters. All right, so this is important here. So again, watch your units, moles per liter. You will quite often see the value also given as a capital M rather than moles per liter. Sometimes we just shorten moles per liter to a capital M, means the same thing, and you'll see that come up in various sources. So the formula for that is concentration equals number of moles N divided by V, volume. Okay, now the way we use this is we generally look for the mass of the solute, or find the moles of the solute from the mass. Okay, and then figure out the moles of the solute, figure out the concentration of the solution from the moles of the solute. So here's a question. We've got a solution containing 6.15 grams of sodium chloride. We're going to dissolve that in 6.00 times 10 to the 3 milliliters of water. 10 to the 3 is 1,000, right? 6,000 milliliters is 6 liters. What's the concentration of the solution in moles per liter? All right. So number of moles, first of all, is mass by molar mass for sodium chloride. So that's 6.15 grams divided by 58.44 grams per mole. Gives us this many moles. We're going to take number of moles now, and we're going to divide by the 6 liters, right? Moles per liter. And we get this value here. So 0.017, however many decimal places, moles per liter. Okay, now significant digits for this one should be based on the 6.15 and the 6.00, 3 significant digits. So 1.75 times 10 minus 2 moles per liter. Okay, notice I went to scientific notation because that's a whole lot easier to get your sig digs properly. Some of your calculators will do that for you. You can actually set them up to do that. Some of your calculators will just go give you the decimal places, and then you manually have to switch over. Okay. All right, so this section is the homework questions that you'll deal with. I'm going to move on to the next topic because we're going to cover two things this week because we need to cover these things a little bit faster. Normally I would cover this in about 2 days, but we may as well move on to the next topic, which is dilutions. So dilutions are simply when you take a solution that has a known concentration and you make it a lesser concentration. So we're going to take our standard solution, which we know the concentration of, and we're going to make it into a smaller concentration. There's two ways to make the standard solutions. One is to dissolve a known mass of a solute in a certain volume of the solution, and then secondly to dilute a known concentration to something that's less concentrated. In class, I would show you a demonstration on how all this is done. Sadly, we can't do that this year. So here's an example. How would you prepare a 1 liter sample of a 0.4 molar potassium permanganate solution from a 1 molar potassium permanganate solution? All right, so the concentration equals the number of moles divided by the volume, or N equals C times V, right? So the number of moles from our known concentration is, or what we're going to need, is the 0.4 times the 1 liter, gives us a 0.4 moles of potassium permanganate. And that's how much we need to put into the other solution. Okay. So the volume of the stock solution then is going to be volume equals number of moles divided by the concentration. So the 0.4 divided by the 1 molar is 0.4 liters. So 400 milliliters is what we're going to need of that solution. Okay. Now, one of the things you want to notice is that the moles in is the same as the moles out, right? So the moles of that we're taking out of the concentrated solution is the number of moles that's going into the less concentrated solution. And so as a result, then we need to understand that. And that makes us, you come up with this dilution equation, which is a whole lot easier to work with. Since the number of moles is the same, we end up with C1V1 equals C2V2. All right, and that's our dilution equation. So if I want to prepare 500 milliliters of a 1.75 molar solution of sulfuric acid from a really concentrated 8.61 molar sulfuric acid stock solution, what volume of the stock solution do I need to dilute? So I'm going to take my really concentrated stuff and I'm going to take a certain amount out of that, put it into a flask, and then I'm going to add water to make up the 500 milliliters, and I want a final solution of 1.75 molar. That's what I'm dealing with here. All right, so what's C1V1? Well, that's what I'm starting with, right? That's the concentrated stuff. And what I'm looking for is how much of that concentrated stuff. So V1 is what I'm actually dealing with. The C2 is the stuff that I'm making, right? That's the 1.75 molar. And when I'm done, I'm going to have 500 milliliters of that. All right, so now we put this in our equation. And then we solve for V1. Sorry, this should be V1. So V1 is equal to C2V2 over C1. 1.75 molar times 500 milliliters is divided by the 8.61 molar, gives us 102 milliliters. So what that means is I'm going to take 102 milliliters of my really concentrated stuff, put it into a 500 milliliter volumetric flask, and then add water to the mark to give me 500 milliliters, and that will have a concentration then of 1.75 molar. This is the capital M I'm talking about before. All right. So it means I'm adding 398 milliliters of water to that 102 milliliters. Okay. All right, and so there's the solution, the questions that you're dealing with on that. That'll keep you busy for this week. Next week we'll move on to our next topic.